So let's move on to acids and bases. So there are two main definitions of acids and bases you guys have to know about. The Arrhenius definition says that acids form H plus in aqueous solutions, whereas bases form hydroxide, OH minus, in solution. So an example of an Arrhenius base would be sodium hydroxide. If you dissolve this in water, it'll produce hydroxide, OH minus ions. The next is the Brønsted-Lowry theory. So the Brønsted-Lowry definition of an acid is that acids donate protons, whereas bases accept protons. Protons, H plus and H3O plus, you'll see later on, are all the same thing. So I can call this H plus or proton, it all means the same thing. So an example of a Brønsted-Lowry base would be ammonia. Solutions of ammonia are basic, but as you'll see, there's no hydroxide, there's no OH to come from ammonia. So there must be some other explanation. So over here, we'll talk about conjugate pairs in a second, but over here I've drawn out the reaction, the acid-base reaction, between the base ammonia and water, which can, under certain circumstances, act as an acid or a base. So in this case, it's going to act like an acid. So according to the Brønsted-Lowry theory, bases are proton, H+, acceptors, whereas acids donate H+. So if ammonia is our base, it's reacting with water as our acid, it's going to accept a proton, an H+, to form ammonium, NH4+. And it's going to accept that H+ from water, which is going to lose one, to become hydroxide, OH-. So in this way, you'll see that we're going to produce OH-, which will make the solution basic. So conjugate pairs. So conjugate pairs happen when a reaction can go both ways. So in this case, we have our base, ammonia, and if we're looking at it in the opposite direction, ammonium, if we were going that way, we'll have to lose a proton, an H+, to become ammonia. So that would make ammonium, NH4, our conjugate acid because it can donate an H+. It's going to donate that H+ to hydroxide, OH-, to become water. So our base over here, our conjugate base over here, is related to the acid. So just note that there is always going to be a relationship between a base and a conjugate acid, and the acid and its conjugate base. We'll get into that more in a second. So first, I just want a refresher for you guys to talk about the properties of acids and bases. So acids, remember, taste sour, whereas bases taste bitter. That's why sometimes if you get soap in your mouth, it tastes a little bitter. So both of them are conductive. So if you try to run a current through them, both of them will work. Acids can be characterized by dropping a bit of litmus paper in there, and it should turn red if it's an acid, and blue if it's a base. Remember, acids are, by definition, they have a low pH, so somewhere between 1 and less than 7, whereas bases have a high pH, so 7, higher than 7 to 14, where 7 is considered neutral, so water has a pH of 7. Acids don't really have any characteristic feel, whereas bases feel slippery. So again, as an example, soap. So let's move on and talk about strong versus weak acids and bases. So strong acids or bases dissociate completely in solution, whereas weak acids or bases dissociate only partially. So if we take a look at our equation here, this over here is acetic acid, which is found in vinegar, and it's reacting with water, which is acting as a base right now. So acetic acid, which by definition is an acid, will donate one proton, H, to water to give H3O plus and acetate. So if we look at the acid-base, conjugate-base relationship, acetic acid is our acid, water is our base, H3O plus, hydronium, is going to be our conjugate acid, and acetate is going to be your conjugate base. So this reaction only happens about 1% of the time, which means that 99% of the acetic acid that we have has not dissociated. It's going to stay as acetic acid. Only 1% is going to go on to form this acetate. So that means it won't dissociate completely. Strong acids, which I've listed over here, will dissociate completely. So this arrow is essentially one way. It will all form H+, it will all form Cl-. If I react HCl with water, it's all going to go on to form H+ and Cl-. An important thing to note, as a reminder, is whenever I say proton or you see proton written down, it's the same as H+, which is more or less the same as H3O+ or hydronium. They're all used interchangeably, and they're all a way of measuring the pH, which we'll get into in a second.